Class 10th Chapter 1 Real Numbers.
Exercise 1.1. Express each number as a product of its prime factors. Problem 1. 140. To find prime factors, we perform repeated division starting with the smallest prime number, 2. 140 divided by 2 equals 70. 70 divided by 2 equals 35. 35 divided by 5 equals 7. 7 divided by 7 equals 1. The factors are 2257 is equal to 2 square 57. Problem 2. For 156. 156 divided by 2 equals 78. 78 divided by 2 equals 39. 39 divided by 3 equals 13. 13 divided by 13 equals 1. The factors are 313 is equal to 2 square 313.
Problem 3. For 3825. Since 3825 is odd, we check divisibility by 3, sum of digits, 3 plus 8 plus 2 plus 5 is equal to 18, which is divisible by 3. 3825 divided by 3 equals 1275. 1275 divided by 3 equals 425. 425 divided by 5 equals 85. 85 divided by 5 equals 17. 17 divided by 17 equals 1. The factors are 3 into 3 into 5 into 5 into 17 is equal to 3 square 5 square 17. Problem 4. For 5005. We test primes sequentially, 5, 7, 11, and 13. 5005 divided by 5 equals 1001. 1001 divided by 7 equals 143. 143 divided by 11 equals 13. 13 divided by 13 equals 1. The factors are 5 into 7 into 11 into 13. Problem 5. For 7429. This number does not have small prime factors. Testing larger primes. 7429 divided by 17 equals 437. 437 divided by 19 equals 23. 23 divided by 23 equals 1. The factors are 17 into 19 into 23. Problem 2. Find the LCM and HCF of the following pairs of integers and verify that LCM into HCF is equal to product of the two numbers. Problem 1. 26 and 91. Step 1. Prime factorization. 26 is equal to 2 into 13. 91 is equal to 7 into 13. Step 2. Calculate HCF and LCM. HCF, the common factor, is 13. Thus, HCF is equal to 13. LCM, 2 into 7 into 13 is equal to 182. Thus, LCM is equal to 182. Step 3. Verification. LCM into HCF is equal to 182 into 13 is equal to 2366. Product is equal to 26 into 91 is equal to 2366. Since 2366 is equal to 2366, the relationship is verified. Problem 2. 510 and 92. Step 1. Prime factorization. 510 is equal to 2 into 3 into 5 into 17. 92 is equal to 2 square into 23. Step 2. Calculate HCF and LCM. HCF, the common factor, is 2. Thus, HCF is equal to 2. LCM, 2 square into 3 into 5 into 17 into 23 is equal to 23,460. Thus, LCM is equal to 23,460. Step 3. Verification. LCM into HCF is equal to 23,460 into 2 is equal to 46,920. Product is equal to 510 into 92 is equal to 46,920. Since 46,920 is equal to 46,920, the relationship is verified. Problem 3. 336 and 54. Step 1. Prime factorization. 336 is equal to 2 power of 4 into 3 into 7. 54 is equal to 2 into 3 cube. Step 2. Calculate HCF and LCM. HCF, common factor are 2 and 3. So 2 into 3 is equal to 6, thus HCF is equal to 6. LCM, 2 power of 4 into 3 cube into 7 is equal to 3024. Thus, LCM is equal to 3024. Step 3. Verification. LCM into HCF is equal to 3024 into 6 is equal to 18,144. Product is equal to 336 into 54 is equal to 18,144. Since 18,144 is equal to 18,144, the relationship is verified. Problem 3. Find the LCM and HCF of the following integers by applying the prime factorization method. Problem 1. Prime factorization of 12, 15, and 21. We express each number as a product of its prime factors. 12 is equal to 2 into 2 into 3 is equal to 2 square into 3. 15 is equal to 3 into 5. 21 is equal to 3 into 7. HCF, the product of the smallest power of each common prime factor. HCF of 12, 15, 21 is equal to 3. LCM, the product of the highest power of all prime factors involved. LCM of 12, 15, 21 is equal to 2 square into 3 into 5 into 7 is equal to 4 into 3 into 5 into 7 is equal to 420. Problem 2. Prime factorization of 17, 23, and 29. These numbers are all prime numbers. 17 is equal to 17. 23 is equal to 23. 29 is equal to 29. HCF, since there are no common prime factors, the HCF is 1. HCF of 17, 23, 29 is equal to 1. LCM, the product of these prime numbers. LCM of 17, 23, 29 is equal to 17 into 23 into 29 is equal to 11339. Problem 3. Prime factorization of 8, 9, and 25. We express each number as a product of its prime factors. 8 is equal to 2 into 2 into 2 is equal to 2 cube. 9 is equal to 3 into 3 is equal to 3 square. 25 is equal to 5 into 5 is equal to 5 square. HCF, since there are no common prime factors among the three numbers, the HCF is 1. HCF of 8, 9, 25 is equal to 1. LCM, the product of the highest power of all prime factors involved. LCM of 8, 9, 25 is equal to 2 cube into 3 square into 5 square is equal to 8 into 9 into 25 is equal to 1800. Problem 4. Given that HCF of 306, 657 is equal to 9, find LCM of 306, 657. Step 1. Using the relationship between HCF and LCM. For any two positive integers a and b, the product of their HCF and LCM is equal to the product of the numbers themselves. This is expressed by the formula. HCF of a, b into LCM of a, b is equal to a into b. Given the values a is equal to 306, b is equal to 657 and HCF is equal to 9, we rearranged the formula to solve for the LCM. LCM of 306, 657 is equal to 306 into 657 divide 9. Step 2. Performing the calculation. To find the value, we can first divide 306 by 9 to simplify the multiplication. 306 divide 9 is equal to 34. Now, multiply this quotient by the second number. LCM is equal to 34 into 657 is equal to 22,338. The LCM of 306 and 657 is 22338. Problem 5. Check whether 6 power of n can end with the digit 0 for any natural number n. No, the number 6 power of n cannot end with the digit 0 for any natural number n. To understand why, we apply the prime factorization method. Step 1. Divisibility rule for 0. For any number to end with the digit 0, it must be divisible by 10. This means its prime factorization must contain both 2 and 5 as factors. 10 is equal to 2 into 5. Step 2. Prime factorization of 6 power of n. The prime factorization of 6 is 2 into 3. Therefore, 6 power of n is equal to 2 into 3, power of n is equal to 2 power of n into 3 power of n. Step 3. Absence of factor 5. The prime factors of 6 power of n are only 2 and 3. The number 5 is not present in the factorization. Step 4. Fundamental theorem of arithmetic. This theorem states that the prime factorization of every composite number is unique. Since 5 is not a factor of the base 6, it will never appear in the factorization of 6 power of n regardless of the value of n. Conclusion: since 6 power of n does not have 5 as a prime factor, it is not divisible by 10 and therefore never ends with the digit 0. In fact, 6 power of n always ends with the digit 6 for any natural number n. Example: 6 power of 1 is equal to 6, 6 power of 2 is equal to 36, 6 power of 3 is equal to 16. Problem 6. Explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. Step 1. Analysis of the first expression. A composite number is any positive integer greater than 1 that has more than 2 factors. We can simplify the expression 7 into 11 into 13 plus 13 by taking out the common factor 13 using the distributive property. 7 into 11 into 13 plus 13 is equal to 13, 7 into 11 plus 1 is equal to 13, 77 plus 1 is equal to 13 into 78. Since the number is a product of two integers greater than 1, 13 and 1978, it has factors other than 1 and itself, making it a composite number. Step 2. Analysis of the second expression. Similarly, for the expression 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5, we can factor out the common term 5. 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 is equal to 5. 7 into 6 into 4 into 3 into 2 into 1 plus 1 is equal to 5. 1008 plus 1 is equal to 5 into 1009. Because the resulting number can be expressed as the product of 5 and 1009, it possesses more than 2 factors. Therefore, it is a composite number. Conclusion: both numbers are composite because they can be factored into a product of multiple integers greater than 1. Specifically, 7 into 11 into 13 plus 13 equals 13 into 78 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 equals 5 into 1009. According to the fundamental theorem of arithmetic, any number that can be expressed as a product of prime factors other than 1 and itself is composite. Problem 7. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time, and go in the same direction. After how many minutes will they meet again at the starting point? Step 1. Identify the mathematical requirement. To find the time when both Sonia and Ravi will meet again at the starting point, we need to find the smallest number that is a multiple of both their individual lap times. This value is the least common multiple, LCM, of 18 and 12. Step 2. Prime factorization of the times. We express the time taken by Sonia and Ravi as a product of prime factors. Time taken by Sonia 18 is equal to 2 into 3 into 3 is equal to 2 into 3 power of 2. Time taken by Ravi, 12 is equal to 2 into 2 into 3 is equal to 2 power of 2 into 3. Step 3. Calculate the LCM. The LCM is calculated by taking the product of the highest power of every prime factor present in the numbers. Highest power of 2 is 2 power of 2. Highest power of 3 is 3 power of 2. LCM, 18, 12, is equal to 2 power of 2 into 3 power of 2 is equal to 4 into 9 is equal to 36. Conclusion: Sonia and Ravi will meet again at the starting point after 36 minutes. Exercise 1.2. Problem 1. Prove that square root of 5 is irrational. To prove that square root of 5 is irrational, we use the method of proof by contradiction. Step 1. Assume the opposite. Let us assume that square root of 5 is a rational number. Step 2. Express as a fraction. If square root of 5 is rational, it can be written in the form a divide b, where a and b are integers, b not equal 0, and a and b are coprime. They have no common factors other than 1. Square root of 5 is equal to a divide b. Step 3. Square both sides. 5 is equal to a square b square. 5b square is equal to a square. Step 4. Analyze divisibility. This equation shows that a square is divisible by 5. According to the fundamental theorem of arithmetic, if a prime number, 5, divides a square, it must also divide a. Therefore, we can write a equals 5c for some integer c. Step 5. Substitute back into the equation. 5b square is equal to 5c square. 5b square is equal to 25c square. Divide both sides by 5. b square is equal to 4c square. Step 6. Conclude a second divisibility. This shows that b square is also divisible by 5, which means b must also be divisible by 5. Step 7. Identify the contradiction. We have shown that both a and b are divisible by 5. This means 5 is a common factor of a and b. This contradicts our initial assumption that a and b are coprime. Conclusion: since the assumption leads to a contradiction, the assumption that square root of 5 is rational must be false. Therefore, square root 5 is an irrational number. Problem 2. Prove that 3 plus 2 square root of 5 is irrational. To prove that 3 plus 2 square root of 5 is irrational, we use the method of proof by contradiction. Step 1. Assume the opposite. Assume 3 plus 2 square root of 5 is a rational number. Step 2. Express as a fraction. If it is rational, it can be expressed in the form a divide b, where a and b are integers, b not equal to 0, and a and b are coprime. 3 plus 2 square root of 5 is equal to a divide b. Step 3. Isolate the radical. Rearrange the equation to solve for square root of 5. Subtract 3 from both sides. 2 square root of 5 is equal to a divide b, 3. Is equal to a, 3b divide b. Divide both sides by 2. Square root of 5 is equal to a, 3b divide to b. Step 4. Analyze the results. Since a and b are integers, a, 3b, and 2b are also integers. Therefore, the right-hand side, a, 3b divide to b is a rational number by definition. This implies that square root of 5 must also be rational. Step 5. Identify the contradiction. This result contradicts the established fact that square root of 5 is irrational. The contradiction arose from our initial incorrect assumption that 3 plus 2 square root of 5 is rational. Conclusion: since our assumption leads to a contradiction, it must be false. Therefore, 3 plus 2 square root of 5 is an irrational number. Problem 3. Prove that the following are irrationals. Problem 3.11 Divide square root of 2. Let us assume that 1 divide square root of 2 is a rational number. Express as a fraction. If it is rational, it can be written as a divide b, where a and b are integers, b is not equal to 0, and a and b are coprime. they have no common factors other than 1. 1 divide square root of 2 is equal to a divide b. Invert the equation, taking the reciprocal of both sides gives square root of 2 is equal to b divide a. Since a and b are integers, the right-hand side b divide a is a rational number by definition. This implies that square root of 2 is also rational. This contradicts the well-known fact that square root of 2 is irrational. Optionally, you can prove square root of 2 is irrational by showing b square equals to a square leads to both a and b being divisible by 2, which contradicts their being coprime. Conclusion: because the assumption leads to a contradiction, it must be false. Therefore, 1 divide square root of 2 is an irrational number. Problem 3.27 Square root of 5. Let us assume that 7 square root of 5 is a rational number. Express as a fraction. If it is rational, it can be written as a divide b, where a and b are integers, b is not equal to 0, and a and b are coprime, they have no common factors other than 1. 7 square root of 5 is equal to a divide b. Isolate the radical, divide both sides of the equation by 7 to solve for square root of 5. Square root of 5 is equal to a divide 7b. Since a, b and 7 are all integers, the product 7b is an integer. This implies that square root of 2 is also rational. By definition, a fraction composed of integers, where the denominator is non-zero, is a rational number. Therefore, the right-hand side, 1 divide 7b is rational. This equation implies that square root of 5 is rational. However, it has already been proven that square root of 5 is irrational. Since a rational number cannot equal an irrational number, our initial assumption is incorrect. Conclusion: since the assumption that 7 square root of 5 is rational leads to a contradiction, the assumption must be false. Therefore, 7 square root of 5 is an irrational number. Problem 3.36 plus square root of 2. Let us assume that 6 plus square root of 2 is a rational number. Express as a fraction. If it is rational, it can be written as a divide b, where a and b are integers, b is not equal to 0, and a and b are coprime, they have no common factors other than 1. 6 plus square root of 2 is equal to a divide b. Isolate the radical, rearrange the equation to solve for square root of 2. Square root of 2 is equal to a divide b minus 6. To combine the terms on the right side, find a common denominator. Square root of 2 is equal to a minus 6b divide b. Since a, b and 6 are all integers, the expression a minus 6b is also an integer. By definition, a fraction composed of integers, where the denominator is non-zero, is a rational number. This implies that square root of 2 must be rational. Therefore, this results in a contradiction because square root of 2 is an irrational number. A rational number cannot be equal to an irrational number. Conclusion: since our initial assumption leads to a contradiction, the assumption that 6 plus square root of 2 is rational must be false. Therefore, 6 plus square root of 2 is an irrational number.